Okay, so first we are going to introduce calculus in machine learning, right? So what is calculus? Calculus is the mathematical study of continuous change. So it's a way to measure the change of your function. There are two major branches of calculus. First is the differential calculus, and the second part is the integral calculus. So differential, as the name suggests, is measure the change of a function, change rate, the difference of a function. And the integral is more about calculate the area of a function, right? Under a function. And in machine learning and the deep learning, we mainly use differential calculus in machine learning. So here's the definition of derivative. So first we define a function of real variable, f of x. The function is differentiable at a point x if its domain contains an open interval and the limit exists. So you need to have a continuous interval at the point x to make the real value to make f of x differentiable. So here's the definition of derivative. There are two kinds of measurement. It's all about measure the change. So to measure the rate of change, first we need to add a small difference, right? A delta x. We will add a small change to the variable x, and we will calculate when the difference approach zero, right? Also limit approach zero. So we want our change difference as small as possible, change of x. So once it's approach zero, we can calculate a new function of f of x. So the derivative we can also call the f prime of x. F prime. So there are two ways to measure the change. First, the first definition is only add a small change to the function, original function. Second one, add a small difference, small change to x. Also, it will subtract a small change of x, and then divide by 2 times delta x. Also, this definition is more common. Is this definition more common? Okay. Okay. So, any questions? No. To do more interaction, I will call your name later to ask your opinion. Hi. Good. So, so the geometrical definition of the calculus is the average rate of change of y respect to y. As you may learn in high school, the change rate of this curve. So the f of x, y is a curve. The rate line is a function, and we want to find the change rate at the point x0. So calculate the derivative at point x is equal to find the tangent line or tangent line, the sect with the curve function, right? So here's using the tangent line, or we can calculate the difference of x, also the change of y. The change of y divided by change of x is the derivative of x at x0. So here are the basic rules. You can use the definition of derivative to derive those functions. The first one is the most basic. X to the power of a, calculate the derivative of x to the power of a will become a multiplied by x to the power of a minus 1. So basically, you move the power number as a constant, and then minus 1 of the original power. And one spatial equation is that the ex, the derivative of ex, is the same as its original value. So it doesn't change e to the power of x. So that's why we love the natural log, right? The natural constant e, because it doesn't change. after the derivative. Okay. So other rules are just for your reference. We are not going into the details of the rules. Okay. Okay, so let's implement the differentiation using programming. So first, as I say, we prefer this definition of derivative, right? We use a small value change. And in practice, we don't need to derive the formula. We just only, if we want to implement in Python or C++ or in any language, we just use a small value to replace the delta. And that's enough to calculate the derivative. So the definition can be changed, or you can replace the data with a small value, and the 0.001 is considered small enough. So using this formula, we can directly calculate the derivative. We don't need to derive the formula of the function f of x. So here's the code. So here we show how to implement. This is our first derivative function. First, we would like to accept a function input. So this is a function pointer. In Python, the function pointer is called a callable or callable function. And once we get the function and a delta small value, we have a default value 0.001. And the input, we can calculate the derivative using the definition, right? So I can give you an example. So this one is f of x, right? This callable function is our f of x. ND array is our vector or matrix. And this is our input. So for this function, it's f of x with the input x plus the delta, right? And delta is just a small value. So we don't need to calculate using the derivative function. Minus, okay, I can write the number 0.001. So the delta is the 0.001. And then divide by 2 times 0. So that's it. That's how we implement the derivative function in deep learning framework. Okay, so divide. So now we know that the neural network is multi-layer, right? Each layer is a function. So we need to implement the nested function. And no problem. So first we can pass an array of function. Pass an array of function. Yes. Any problem? Okay, and then we can call we can just use the chain rule to call function. So for nested function, we just pass the output of function 1 to the function 2. And then so we pass the chain rule chain function, and okay, so we can return the function f of x of 1, just like the math formula in our code. So for the chain function of 2, we pass the function array. The chain is the list of function, pass the function array, and then we just call it. Okay. Because this is an array, so we can use f1 and f2 to represent the function and use the nested function. Okay. That's it. So what's chain rule? We have heard this many times, right? It's very important for deep learning because we have multiple layers, and with chain rule, we can directly measure the change of the total neural network. So chain rule is actually a formula that expresses the derivative of the composition of two differentiable functions, or f and g, in terms of the derivative. In other words, it says that you can calculate the derivative of first function, and then calculate the derivative of second function, and multiply them together. So it's have an intuitive explanation. Intuitively, the chain rule says that knowing the change rate of d of x allow one to calculate the change rate of d of x as the product of the two change rates. Okay, so I have an example. This sentence is a little bit long. So it's from the Wikipedia. So somebody says, Siemens says that if a car travels twice as fast as the bicycle, and the bicycle is 4 times as fast as a working man, right? So actually, we can calculate the car's speed is 2 times 4, 8 times as fast as the man. So that's the basic idea of chain rule. So here's the illustration of the chain rule. So in practice, to implement the neural network framework, we will usually use the graph or computational graph to represent the functions. So the derivative of the composition function should be a sort of product of the derivatives of its own constituted functions. So basically, this is the same thing as previous slide, but just use the picture to represent. So it says that for function f1, the one small change will increase by 3, and for function 2, one small unit will change by -2. Ignore the output, and then finally the f1 of f of 2 will be the 3 times -2, right? So this is the idea of chain rule. It will consider the change of each function and do the multiplication, right? So the change rate 3 will multiply by the change rate 2, right? Then you will get the new change rate. So again, so we will try to implement the chain rule as we have seen in previous. In previous, we calculate f of 2 of f1, right? This is called a forward pass because we just calculate the first output of the first function and we pass into the second function. So this is forward pass. And now we are ready to calculate the backward pass. So to calculate the derivative, we will first assume that we have a first function u is equal to f1 of x, right? And then we calculate the derivative of f of 2 against the f of 1, and then we calculate the derivative of f1. Should be x. So, but as we know, we don't need to calculate directly. We just call our derivative function. So for the first of the f1 dx, we just calculate f1 input. And then for the f1 dx, this should be x. The f1 dx, we call the derivative function of the output f1 against our input. Input is x. So this is our first df1 dx. The second one is just pass the output of f1, right? f1x to the f2 function. So the second one is the f2, the u now represent f1 of x, and then finally just multiply those two functions together. So this is how we implement the chain rule in Python. So we demystify, right? Demystify the myth behind the deep learning framework. So let's see an example. Suppose we have two functions, a square function and the sigmoid function, and we want to do the nested function. output. So sigmoid function, as you know, is the activation function of most deep learning layer. And suppose we have a square input. So here I show the shape of a square function. My function shape is a square, right? As the x go up, the y is equal to f of x. Y is equal to x squared. And this one is the sigmoid function, right? Sigmoid function. So sigmoid output of sigmoid function between 0 and 1. So let's see what happens if we want to calculate a nested function. Here's the code. So we will calculate 2 times of output. The first one is the sigmoid f1 is square, and then f2 is sigmoid function. We will try different order of the 2 functions. The second one is sigmoid first, right? Suppose sigmoid is the second function and the first function later. And we will visualize plot the chain. We will send a range of number. We will pass a range of number into our functions and plot the result. So we have 2 combinations. The first one is square first, square first and the sigmoid function. Second chain is sigmoid first and the square later. And then we plot those 2 functions to see if our implementation of the derivative is correct or not. Okay, so yeah, so here is the results. So first one, the blue line is the output of our nested function. So originally it's a square, right? Square function, but once it's passed through the sigmoid function, because the sigmoid function is between 0 and 1, right? So you can see that original function is like this. Original square function is like this. But once we pass to original square functions, U shape. But once we pass through sigmoid function, it will be between 0 and 1. Between 0 and 1. So first, the function is correct. And then we see the derivative. The second part is the derivative. So we can roughly see that as long as the function output passes 0, then we will have a positive derivative rate. Otherwise, we will have a negative derivative rate. Right? Okay. So, and okay, the second one is just the square of the sigmoid function. So the shape becomes, I would say, sharper, right? The shape becomes sharper. Originally is s, but it's squared. It's still between 0 and 1, but the shape becomes sharper. Original maybe like this. So yeah. So the derivative, we will see that between the 0 point, the change rate increase, the derivative increase. But when it's approached to 1, change rate becomes smaller. So the derivative value becomes smaller. So let's illustrate the implementation of our nested functions. So we can use use the definition of derivative at a small value. We can implement the derivative of functions of our neural networks. So how about we implement a longer chain rule, longer chain rule function? Suppose we have 3 functions, and the first f of 1, and the f of 2, and the f of 3 function. Again, we can use chain rule. Right, chain rule. So we first do forward calculation, right? We will do it forward calculation. We calculate the f1 and the f2 of f1. That's the easy part. right? And the f3, right, of f2 of f1. So this is the easy part, and then we do the back propagation, do the backward calculation to calculate the derivative. So here are the function. So we first do the forward part, and then we calculate the backward part, right? So first this is backward. So we need first to calculate the output of the forward part, and then we calculate the derivative, backward derivative. And then finally we multiply, just multiply the derivative together. Okay. So yeah, that's it. And yeah, so once we got the derivative, we can multiply it together. As remember, the chain rule is about to multiply the change rate of each derivative, right? So let's just multiply them together. So again, we can visualize our nested function. Today, the leaky rate rule always have small value after the zero, and then square sigmoid function. So actually, the leaky rate rule is not continuous at point 0. Okay, remember rate rule function. Rate rule function means that y is equal to x if the output, if the input is larger than 0, otherwise, equal or otherwise, right? So the leaky rate rule is like this. The rate rule, right? Rectify linear unit. Rate rule doesn't consider if the input is less than 0. But leaky rate rule will have a small value if x is smaller than 0. So let's can avoid the gradient vanish problem. And in fact, it's not continuous at point 0, but it's okay because we just implement the derivative function using the definition, and you just assign 0 to that point. Previously, people prefer the continuous function at the differentiable at every point. Somehow, researchers find that with the rate rule, how it's simpler, right? And the leaky rate rule will help you to have a better performance in deep learning. Okay. So now we know how to implement the derivative function with only one variable. How about we have two variables? In fact, in deep learning, we have a vector, or we have multiple variables. So let's start with two. So for two variable, actually you can do partial derivative. In other words, you can ignore one of the value, right? You can ignore x. You can ignore y. You can make y as a constant first. It's like a scalar. So once you do the, which means you keep a constant value and the y doesn't change, then you consider the change of x first. So we will have two derivative. We will have two derivatives. One is d alpha dx, and another one is we will have two value. If we have two input, then we will have two derivative. One is alpha versus x, another one is alpha versus y. Okay, so we will have two derivative for if we have two inputs. Three inputs. Okay. So yeah. So I think this should be U. So the first will be derivative against the O alpha function, or sigma against the alpha function. And then we will do partial derivative for variable x and the variable y. So what is partial derivative? It's very important for deep learning. Partial derivative of a function of several variables is derivative with respect to one of those variables. Okay. So with others hold constant. So it's a derivative with one of the variable. So we can do it one by one. So here's an example from Wikipedia. First, you suppose we have two variables, x squared plus x times y plus y squared. And then we do partial derivative with respect to x, with respect to x. Then we can see y is constant. So because y is constant, we can remove the constant. And the xy is just x is become 1, right? So it will be y plus the derivative of x squared is 2 times x. So that's the derivative, partial derivative of f of x df dz dx or dz dx. Or this is 2, not z. Okay, so you can do the same thing with y. So the y will be x plus 2y, right? So with partial derivative, we can do one derivative one by one for all the variables in your vector. So what's the geometrical meaning of this partial derivative? So here's a picture. So a function with two variables will be a three-dimensional function. This is a 2D plane. And the partial derivative will be this plane. You will get a plane at the point 1, 1. This plane is defined by 2x plus y. Right. So partial derivative will fix one dimension, the calculated change. So finally, the derivative will be equal to this tangent line, the black line on this function, right? So the slope is s. So the slope is equal to 3 at the point 1, 1. You can calculate the result. So gradient, we always heard about the gradient descent of optimization, right? So actually gradient is partial derivative of all the variables inside a vector. Okay, so now you know what is the partial derivative. So that's why our computer can do the derivative all parallelly, right? So it can do partial derivative to variables one by one. And in fact, the chain rule has a particular elegant statement. It says that the total derivative of the composite function can be the partial derivative multiplication. But I will omit the details. You can read the Wikipedia. So sometimes, because partial derivative does not consider the relationship between two variables. If all the variables are independent, you can confidently do partial derivative. However, sometimes we need to want the total derivative. We want to also consider the relationship between two variables. And chain rule says that you can multiply the changes of two partial derivatives. So that can be the composite function can be a total derivative. Okay. So anyway, let's go back to our original problem. To calculate derivative of the two functions, the chain rule for two functions that we can do it one by one, right? So for our original function, f is y plus x plus y, for the function x plus y, we will calculate twice. We will have two sub functions. And you can have a tree to find all the possible derivative. Also, suppose we have two nested function and have two variables, we will get 4 partial derivative as the tree shows. So luckily, the deep learning framework will do this for us. So how can we implement the derivative of two input functions? And first, we calculate the f of x, the f dx, right? And then you multiply by the partial, yeah. So it will calculate the function of x plus y, right? First, and then multiply by the change of dA dx, dA dx. And dA dx is actually is equal to 1. Right? It's partial derivative of x, so y is constant. It's only 1. So again, the same thing for df dy. So finally, we only have derivative of sigma, right? Because the partial derivative of input is 1. So let's simplify our task. dA dx and the dA dy are all equal to 1. But now, as we know, because it's two inputs, so we will return two derivatives, partial derivatives. But we can calculate total derivative of our sigma function, of our function x plus y. Is our forward function. And then we pass to sigma. Remember, this is equal to sigma plus our f of x. Okay. Sorry, I should use the same. Function, also sigma plus the a of xy. Right. Yeah, so just paste the function a into the derivative, and we can get the partial derivative. Okay, so finally, we consider the vector or derivative of multi-input functions. So it's a dot product. It's a concise way to represent the many individual operations. Okay, and yeah. So as you know, the matrix multiplication can be considered as a lot of dot product, right? So for multi-input, like a vector, right? We can use dot product to calculate the result, concise way to calculate. And as we know, the gradient is partial derivative, right? And for partial derivative, we ignore the others. So suppose we want to calculate y is equal to wx, the most common formula. W is the weight of the deep learning layer, and x is the input. And then we calculate derivative one by one for each variable in x. And then we can actually totally ignore other weight. So dy dx is actually w1, w2, w3. And finally, you can see that dy dx, suppose this is y, will become the weight vector x. So it's very similar to single variable, right? So that's we can comfortably use a vector to represent our data and then calculate the result. So vector functions as their derivative, we can see like this. So first, now we use dot product to represent our multiplication of that product. And then, so actually it's a two variable output. And then we go back the backward calculation. And luckily, the backward derivative is actually the transpose of weight vector, WT, dN dx. And it's a forward extra. The forward extra will be the product. And this is our forward function here. So the backward will just the transpose of W vector. Okay. Okay, so the vector functions and their derivative will be dot product first, and then the backward calculation of the function n. N is the dot product of x and w, and multiplied by the dn dx, or the is missing dn dw. Dn dw will be x transpose. And finally, we multiply those two together. This is one way. This is one backward loop path. So this is backward one. Backward one is this path. We will have backward two. You can implement backward two together. Okay, so backward one is the dsd multiplied by dn dx, right? Dn. Okay, so this is path backward one. So so we want to extend to 2D matrix or tensor, right? But things become a little bit more complicated because now we are dealing with matrix. So how can we use the chain rule? So well, I will say the most important thing is this style of code. So for gradient regarding matrix output, we need to sum the final array into a sequence. Because we are all finally we care about how much the final output change if we change one of the variable, right? And now we got a matrix. So the solution is to sum the output vector together. Sum the output. We calculate again like the previous. We calculate the partial derivative one by one, and then we then sum them together. So for higher dimension, usually we need to sum them, make a summation of the products, and then we will get the value to represent the change rate of our function. So that's a rough idea. So in practice, you will find the sum summation function, or you will call the sum function to sum output. So now our output is a matrix, and we need to add them together. So that's it. That's how we deal with higher matrix input and output. Okay. So because now the output is a matrix, so then we need to sum all the elements. Okay. So other things are the same. Other things are the same. Optimization is actually a very rough term. So we try to optimize. In other words, we try to minimize our error, right? So in terms of error rate, the best optimization is to minimize the error. So you will see the first word minimize. It will try to minimize the output of a function f of x. Usually is error function, right? Cost function. And then we will give the function some constraints. It will substitute some like, okay, so our input will need to between -1 and 1, something like that. So we can give them some constraint. And this is the standard form of a continuous optimization problem. F is usually called the objective function to be minimized. And there are inequality constraint or equality constraint. So this is optimization function. It's just define our goals and how to implement them will depends on different areas. So usually we will see min, right? Because minimize is too long. People will say min. And the min will with a dot. Sorry. I mean, usually we will write the min with a dot. The dot means this the abbreviation of minimize. It's not just the min, minima. It's a verb. Okay. So okay, so let's look at the most familiar optimization method, so gradient descent. So it's actually proposed by Koch in 1947, almost 200 years ago. So suppose we have a function which is f of x, the blue line is our function, and then we want to, we randomly select a point like 0. For this function, we have a perfect minima, global minima at x equal to 0. You can directly derivative of f prime of x. This kind of function is called convex optimization. It's a convex function which has a global minima. If your function has a global minima, it's called convex function. But in practice, usually we don't know where to go. In practice, we know the function is very complicated. It's no guarantee there's a global minima. So we will randomly select a point like this, right? And then we will calculate our derivative to find the tangent line. And we will find that the tangent is larger than 0. Which means if we want to minimize our function, we should move forward here in this way. So the gradient descends to minus a value, a small value. The value can be defined by u. The alpha is called the learning rate. You will define how large you need to go. You can define that. The derivative just give us the direction. Where shall we change? Where shall we change? So if the derivative is larger than 0, then you can see that we should be go left side to get the smaller output. So it's so we will subtract learning rate multiplied by f prime. So if it's a subtract, it's a descent. If it's a addition, it's a ascent. Okay, so basically there are three possible results if you get the if your derivative is equal to 0. There are 3 situations. First, it can be the minima, right? So second, it can be the maxima. And the worst case is there's a saddle point is either minima or maxima. It's called a saddle point. It's at the point of change. Okay, so there are 3 possible critical points if you find the derivative is equal to 0. Equal to 0 means that the slope is 0, right? It's a horizontal line. Okay, so as we said before, a real function is very not easy to find the local minima, or it has a lot of local minima. It's difficult to find the global minima. I mean, so when you try to do descent function, right, how you are very easy to get stuck, right? Or you can go down this way, but it's very easy to stuck at this point. Because at this point, you will find it's hard to minimize, to get lower, and also the derivative is almost a 0, so it's very difficult to improve it further. However, we need to find a way to get out of this hole and try to continue to find a better minima. So that's how we propose different kinds of optimization algorithm. Okay, so the second derivative can measure the curvature. So this is a negative curvature. So it's face downward or no curvature at all. If your second derivative is also 0, or positive curvature if your second derivative is positive. To calculate the second derivative, you can use the Hansian matrix. Basically, calculate the different combinations of partial derivatives or second derivatives. Okay, so so as we say before, the derivative is equal if the derivative is equal to 0, it can be minima or maxima point. Also, we can study the second derivative to see if minima or maxima, or again, it's the point of reconvection. Okay. So saddle point, the definition of saddle point is that a point contains both positive and negative curvature. It's like a saddle of horse, so it's why it's called saddle point. An example is that f of x is equal to x1 squared minus x2 squared, right? And it will show you this kind of point. And our okay, so that's the saddle point. And saddle point will make our learning very difficult. So how could the learning go wrong? As we mentioned before, you can decide how far one step to go, right? The learning rate, you can define the learning rate. But if the learning rate is too big, you may go too far, right? So maybe you will go this way. It's a very large learning rate and go this way, or this way. But you find you are getting smaller error, you are improving. But however, the real minima is here. Also, you will get oscillation if the learning rate is too big. So you move quickly in directions with small but constant gradients. So in this case, we should make a smaller learning rate, right? Also, in other point is that in practice we will have usually we have a large training data set, right? If we have a big enough GPU, we can put all the bench inside the memory, and we can do training. We can calculate the gradient of the bench. Then that will be the bench gradient descent. You will quickly go to find a good local minima. But in practice, we cannot put all the data. We cannot calculate the gradient of all data at one time. So we will select a mini bench. It will converge. Suppose slower. Okay, so select bench. You need to similar to the original distribution, right? So usually we need to select multiple times. So it will more diverse, but it will converge. The one of the extremes to select one sample at a time is called a stochastic, like reinforcement learning, but it will be very it's diverse, right? But it will eventually converge. So here's an interesting program that can show us how different the learning algorithm to do with different kinds of structure. Or you can download the code here. So first, how can we overcome this kind of hole? This small hole. Huh? So there are two minima in the picture, in the right picture. So first, we will go from here. There are two learning algorithms. One is original gradient descent, and another one is with momentum. So momentum will consider the change value of your last update. So it's like a running fast, right? It's keep the same speed, same velocity of previous change. And so it will still go fast. And then this can maybe help then overcome some local minima. It's not a guarantee, but it can help you to go through some bad local minima, right? But you can see that gradient descent will stuck at this point because it does not consider momentum. So usually we will add momentum into our formula. So we will first use the previous change delta. You can change your it's called decay rate. It's like learning rate for momentum, and you calculate the new change, and then add the new change to update your weight. So momentum can help you to overcome some local minima. So how there are another way to update the function is called adaptive gradient algorithm. So first is use the sum of gradients squared. Track the sum of gradients squared. And it will in machine learning, because there are so many features, so some features are sparse. then it will make the average gradient small and training is slow. So adaptive gradient will update, first focus on update a set of features and then others. So it will do something like that. It will focus on maybe this direction first, and then make a turn because it's focused on another feature. It will maybe focus on Y first, and then focus on feature X first, and then focus on X2. So it's a make like it's like making a turn. And the improve of the adaptive gradient is root mean square of propagation, root mean square. So root mean square add a decay rate for updating gradient squared. So yeah. Well, it's make learning a little bit faster, and the RMS prop is very popular also. Well, so its contribution is a make decay rate between the new value and the previous square value. So it's a weighted sum of new value, new square value, and the previous value. And ADM consider both the momentum and the RMS prop of square value. So this tool is very interesting. So you can compare the result of different optimization algorithms. And in this experiment, only ADAM can escape the small local minima and find a new local minima. Okay, so yeah. So in practice, we usually select the RMS prop or ADAM. Right, so all about your learning rate and your luck, right? So if you have a good luck, you can find a good local minima. So it's, or I should say, it's about the power of your GPU. If your GPU is very powerful, like always can try more random, try more parameters, and you have better chance to find a better local minima. Okay, so that's our brief introduction of calculus and optimization.